work on to describe the properties of the exoplanets. Okay, so exoplanets. This is the number of exoplanets discovered until 2014. So it's a histogram from beginning in 1989. So first one was discovered in 95, but then we found some more in archival data. That's why we can begin earlier. And what is interesting here is not the number. Well, you see that it's increasing a lot. This is Kepler satellites. Okay? But what's interesting here is the color is with the detection method. It's linked to the detection method. So in green, you have the transit. Okay, so what you see before, in fact, before looking there, you see that it's mainly blue. Blue means radial velocity. Okay, so at the beginning, we only discovered exoplanets with radial velocity. It began to change in 2010 nearly, when it was half and half, half radial velocity, half transit, and now it's mainly only transit. Because it's simpler. You just have to look at the photometric variation. You don't have to build complicated spectrographs to look at the variation of the spectral line. So it's easier. In red, you have the direct imaging. You see that it remains very small. And in orange, you have the micro lensing, not small. Okay? So it's mainly now transit. Yes?
The exoplanets of 1989 and 1992, you said it's from archives, right?
Yes.
Okay. What kind of instruments they gave us?
Well, there were already some, in fact, there were some follow-ups of stars to look for exoplanets for a long time ago. I think it probably began in 1985 or something like this. In fact, the first one that was discovered had an orbital period of 6 months. But this was an artifact. Just because of bad subtraction of Earth's movement. So, yeah, people who were looking for this, they knew that there would be planets. They were just looking for it. So it was difficult. So it's just to think there was the how to say, the precision, the accuracy of the spectrographs, but also the modeling was not very easy to do. So with better models, better computers, better spectrographs, then we could discover planets that were in the archives but that were not found previously. So in '95, when Mayer and Kelos discovered their first planet, some groups went back to archives and found planets up to 89.
The archives are from observations from Earth?
Yes, yeah, because they were, at this time they were, observations from space are just for transits. You cannot build an accurate spectrograph that will go on a satellite. It's too complicated. It's big. Spectrographs are very big. I mean, there are some spectrographs at the European Southern Observatory that are nearly the size of this room. It's big instruments. So you cannot put this on a satellite. And so this is the number of exoplanets. So this was the census yesterday. I looked at this website, exoplanet.eu. At the end, I will give you a bibliography if you want to go further of many websites and things. So there are now 3,565 exoplanets, 2,675 planetary systems. Okay, so stars with planets. 602 multiple systems. So many stars are more than one planet, and these are all the transits seen by Kepler. Okay, so there are many.
So black dots there are the planets, right?
Sorry?
The black dots are
Yes,
the
yes,
planets?
sorry, yeah. The black dots are the transits in front of the stars. So there are many. There was only, they said, the first one was in 95, and 20 years later you have now a huge bunch of planets that you want to characterize their properties, from big planets around big stars to small planets around small stars, or big planets around small stars, or small planets around big stars, etc. etc. Different temperature, different everything. These are the properties. Again, here you have the color coding for the discovery methods. The orbital periods goes to 1 to 10 to the 5 days, and mass goes to 0.1 to 10 to the 3 Earth's mass. And you see that there are 3 big groups. The first one is what we call the hot Jupiters, like the first one discovered in 95. Hot Jupiters are massive planets with short orbital periods. Okay, these are what we call the hot Jupiters, because they are Jupiters but close to the star. Second one are Jupiters. You see that most of the planets are Jupiters. Some are hot, but most are Jupiters. So these are massive planets with long orbital periods. So these ones are detected by radial velocity on transit. This one mainly by radial velocity. Third group is what we call the super Earth. We call also them the hot Earth. So they are like more massive than the Earth. The Earth is here. You see? Oh, sorry, the Earth is here. The Earth is here. So it's one solar mass with a period of 365 days. So the Earth is here. So these are more massive than the Earth, so these are called super Earths. Super just means more massive, and with short orbital periods. And you see that there is a gap, which is this one. This is what we call the hot Neptune, where we now discover some stars, some planets, mainly with the transit method. Yeah, I forgot to mention, you see for the super Earth, most are discovered with the transit method. It's easier to detect because they are not as massive as the Jupiter. In the Jupiter, radial velocity is fine because they are massive. These ones are not as massive, so they are more discovered with the transit than the radial velocity. The hot Neptune are very interesting because we don't know them, mainly because we don't have hot Neptune in our solar system. In fact, this was something I wanted to tell you, but I forgot. But if you look at this, there is something, in fact, it's simpler if we go there. There is something which is very strange, that we have some very small planets, we have some very big planets, we don't have nothing in between. Between 1 and 10 Earth's mass, we don't have anything. This doesn't mean that we cannot form them. This probably just means that it's more difficult perhaps to form, and also it's more difficult to detect, because if it was not more difficult, well, we would have detected them. So there are these parts, hot Neptune, and we want to detect more of them. You see we have some with the transit and the radial velocity, but not many. So Earth is here, Uranus is here, Jupiter, Saturn. Jupiter is inside the Jupiter group, which is nice, but not in the middle. It's not a typical Jupiter planet. And well, there are many missing, and many missing are not because they are not there, probably it's just because we didn't detect them. So for instance here, some long period with the mass of nearly the Earth probably must exist, but we didn't detect them. Yes?
As it concerns the composition of Jupiters and Neptunes are always gas and Earth are rocky planets, or it can vary?
No, yeah, these planets are mainly probably rocky planets. These planets are mainly gas planets. In between, it's not so clear. I will talk a bit about the composition later. We have also some planets which we think are the cores of giant planets. Like all the atmosphere has been ejected. Now for Jupiter, for instance, we have nearly 1/10 of the size is just made of probably very compressed carbon inside, and 9/10 is just gas. So if you take away this 9/10 of gas, are just just have the core, and we think we detected this kind of planet. So we have different composition. I will show you later. Okay, so this again the Earth's mass versus the orbital period or semi-major axis, which is the same, and here you have again the three groups. Here you have the radial velocity, the transit, microlensing, and direct imaging. You see, direct imaging are very far away planets. What's interesting is also is that you have the timing. Timing, you remember pulsars? This is the timing method. So we have some. Just another one to same plot, but here you have the orbital period. Instead of semi-major axis here, we have the orbital period here, and this, instead of having the mass, you have the planet radius. So just to make things more complicated, but just to show you that we always have these nearly three groups here. Here we have the orbital period with the planet radius. One is Jupiter, so you have the hot Jupiters which are here. The other Jupiters are there. The cold Jupiter, if you want. And here is the super Earth. Here. Okay. So one of the questions I said is where are the planets between 2 and 10 Earth masses? 2 and 10, which is nearly here. Okay. In this range. We don't have them in our solar system. Okay, then what's interesting also is that we found many multiple systems. For instance, this is one of the two examples where you have here the Sun, Mercury, Venus, Earth's mass. Here you have 3 planets that are between 75% and 4 times the mass of Jupiter inside the orbital radius of Mars, nearly. Here you have another system of the same type. So many multiple systems with giant planets, very in a compact system. Gaseous planets. So this is what I told you earlier. We have the size of the core here, and here the size of the whole planet for Jupiter, Saturn, Uranus, Neptune. And so now we can begin to work on the models of these planets, where we try to see what is the size of the core compared to the rest. So this is Jupiter with a core of compressed carbon, which could be diamond, because if you compress the carbon out, you make some diamonds. So you could have a core of diamond inside Jupiter, which is quite cool, I think. And then you have probably liquid metallic hydrogen. You have some rains, hydrogen rains on Jupiter, which must be nice also. Probably the umbrella doesn't. It's not sufficient to protect yourself, but there you have some hydrogen, helium envelope. Well, you have some hot exoplanets. So this, for instance, is the hottest exoplanet we know of, an orbital period of 26 hours, so nearly 1 day. Probably temperature is the order of 2,000 degrees on the planet, so nice weather. Big planets. So this is a planet which is 277 mass of Jupiter, with a period of 3.5 days around the star. Massive planets. This is, for instance, Cours. Cours Exo 3b, the size is the size of Jupiter, but the mass is 21 times the mass of Jupiter, which means that it's much more dense. Probably it has a core which is much bigger. Instead of measuring 1/10 of the size of the planet, it must measure probably at least half of the mass of Jupiter. It's 21 times more massive. And then to finish this catalog of exoplanets, you have this what we call the Chtonian exoplanets. Do you know this? I think it's in English must be Chtonian, probably. Not very different. This is a Greek name, so probably it's not very different from French to English. Maybe Chtonian. Chtonian exoplanet is exactly what I said earlier. You take Jupiter and you take away all the envelope, so 90% of the matter of Jupiter, and you just have the core. So it's very compressed core, where you get rid of the atmosphere, just because you took the planet very close to the star. You make a lot of evaporation, and then all the envelope goes away. You just have the core, very heated core. So you can imagine very compressed. You have like thousands bars of pressure on the core. So you have very compressed matter of carbon that you heat a lot when you are very close to the star. So it makes a very peculiar planet, I think. So this is why we call it a Chtonian planet. I think Chtonian means something like hell in Greek. You're not Greek? Yes, you are Greek. So what does it mean?
We don't use this word.
Sorry?
We don't use this word.
Well, I think it's ancient Greek. So
yeah.
but I think I might be wrong, but I think I remember I read that it was it means something like hell or something like this. Probably it is the case.
I can check it.
You can check it and then you tell me. Okay, so we think we found one of these Chtonian planets. Cours B. Cours is one of the satellites that discovered a lot of exoplanets. It's a French satellite.
Yeah, okay. Cours is the underground.
Okay. Yes, well, it makes sense. Well, the hell is below anyway, so.
Yeah.
Okay, so this is the.
And also the core is below.
Yes, yeah, underground, yes. Yeah, sure. This is why I said it makes sense. This is the radius of the. Well, these are different models for this Chtonian planet. This is an artistic view of what it could look like. I think it doesn't look like this at all, because probably because of the pressure, the shape is very round. There is no nothing going up like this, I think. This is the model where you have the radius versus the mass, and you see that this is the model for the iron, silicates, ice, and probably it is a mixture of silicates here. So quite heavy, quite dense. Here you have the model for Jupiter. You see it's very different from Jupiter, much more compact, much denser. So period is 20 hours, 1.7 Earth's mass, so very small. 5 times the mass of the Earth, so much more mass, much more compact than the Earth, with a temperature which is more than 1,000 degrees. Rotation period nearly 1 day. This is the size of this planet. So if it was the core of ex-Jupiter, then you had this inside of Jupiter. What is interesting is that we can follow the. This is the flux in days, and we think there are some solar spots on the surface of the sun. And this is the transit detection, so of this planet passing in front. Okay, Chtonian planet is not very interesting for us to find some life. What is more interesting, what we are looking for, is more like the super Earth. So here you have one super Earth. Super Earth of low density, where you have an orbital period of 1.6 days. So put 2.5 Earth radius, 6.5 Earth mass, with density of nearly 2. And this is the model. Well, the model can change a lot in these planets. So I just show this for an illustration, but obviously it can be completely different of this. I will show you afterwards some different models of particular planet. Here you would have a core of iron and nickel. Then you would have metallic core. Then you have like a rocky mantle. Then you would have some compressed ice, and then you put there a global ocean, a bit like in the film Interstellar, and the movie. I don't know if you saw it, but you have a planet ocean where you have a tsunami every I don't remember what's the orbital period. Where probably you don't have any tsunami in an ocean planet which is close to a black hole, but this I think was for the purpose of the movie. So we don't know any global ocean planet in the solar system. So this comes out from the models. Probably it could exist because there is a lot of water, but this was to explain the structure of this planet and the density, which is much higher than the density of the Earth. Okay, then Gliese, this one. This is an interesting also object because there are two planets which are in the habitable zone that I will describe just afterwards. Just to mention that there are many multiple systems. And I think I will finish with this catalog of the planet with this one. This is Kepler 11. This is an ultra-compact system where you have 6 exoplanets around this system. And the 6 exoplanets are nearly within the orbit of between Mercury and Venus, a bit more than Mercury. So very compact, which shows that, again, that our solar system is not typical at all of most exoplanetary systems. And we can work on the composition of these planets. So this is the radius versus the mass. The Earth is here, and Uranus, Neptune here. And you see, these are the Kepler 11 B, C, D, E, F. And they have mass which is between 1 and 15 Earth masses, something that we don't have in our solar system, because we don't have anything between the Earth and Neptune or Uranus. And this is the radius, sorry. So this is exactly filling the gap that we have in our solar system. We have some planets here that are exactly the mass between the Earth and Uranus that we don't have in our solar system, and that we find in some others. Okay, now I had also Kepler 22. Kepler 22, I just show you some example to show you that we have a huge diversity of exoplanets. Kepler 22 compared to the habitable zone that I will describe later. This is another one which is well, this is an artist's impression. Okay, I will go. Okay, so, I just want to show you that there are many exoplanets. I will not describe all of them. This is Jupiter. So this is not an exoplanet, but all the others are exoplanets, and you see that there are different radius, a big diversity. This is Neptune here, and this is the Earth. Okay. Okay, so big diversity in radius, in mass, etc. Okay, are there some? You have some questions there? Now we will go to the habitability zone and atmospheres before finishing with the observations. Is it okay? Okay, so habitability zone and atmosphere. This is, I think, something that will become more and more interesting now because we have more observations, more accurate observations. So we can now say something about the habitability zone. I didn't describe this, but there are many exoplanets for which it was announced that they were in the habitability zone, and then having more observations the people retracted themselves and said no, in fact they are not in the habitability zone. So there is a lot of there are many debates about many different systems. Habitability zone is not this. The Petit Prince is not in the habitability zone because the habitability zone is a planet who is in the habitability zone must have an atmosphere. If you don't have atmosphere, then you'd have a gradient of temperature which is too different between Earth and the day and the night, and temperature also vary too much, like the moon where it's plus 150 degrees on day and minus 200 during the night. So you have temperature must be maintained between 0 and 40 degrees Celsius, and this allows the presence of liquid water. There is no liquid water on the planet of the Petit Prince. And then we want to find some planets which are in the habitability zone, temperature between 0 and 40 degrees, atmosphere, liquid water, but also we want to have these ingredients for life to emerge, which are what we call the champ in French, are the carbon, hydrogen, oxygen, azote, and sulfur. Also the phosphor can be interesting. Why do we want this? Well, because this is all the ingredients that have allowed to form the life on Earth. So you can say that we are a bit Earth-centric, which is true, but also we know that it has worked on Earth. There are other arguments. For instance, the carbon is a tetravalent atom, so it can have 4 pints, which is not the case of all the atoms. Silicium, for instance, can have this, but the chemical there are not so many molecules made of silicon than carbon. Carbon we detected like more than 100 different molecules in the interstellar medium. So it's an interesting molecule, and in fact when we look at atmospheres of exoplanets, we look at the presence of water, but this we can find everywhere. Even on the comet we find water. Even on Mercury we find water. We don't find liquid water, but we find water, ice water. So we'll try to find water, we'll try to find carbon dioxide, which is a nice molecule to heat the planet. We'll try to find carbon monoxide, which is interesting to know the process of making oxygen. For instance, if you have some photosynthesis and things like this, we try to find ozone. O3 is interesting to protect from the UV of the star. So we try to find some signature like this, which can allow life to form. Obviously, we are not looking for life like us. We are looking for different life, but can be even bacterial or life. Would be interesting to find, at least to know that life is an easy process that can be formed in different planets. The problem with bacterial is that they will not communicate easily. So it's easier, obviously, to find some life with who you can communicate, but this probably is not something which is very common in the universe, or at least we didn't see it. You need some time also, not so long in fact, because for instance on Earth we have the first evidence of life nearly 3.7 billion years ago. So nearly 700 million after the formation of the Earth we had already stromatolites, so bacterial life. So probably life is not so, when you have all the ingredients, probably life is not so difficult to form on Earth, and if we export the idea also elsewhere. Okay, so the habitability zone depends on the star, because if you have some hot stars, it's better to be far away from a star. If you have faint stars, it's better to be close to a star. So the green zone is the habitability zone. It doesn't mean that you cannot have a planet outside the habitability zone, for which you can have some life. But in this case, you need to find another source of heating, which can be internal heating, which can be tidal heating, which can be, for instance, a satellite close to a giant planet, like Europa, Enceladus, or Titan in our solar system. But you cannot have only the heat from the star. Okay, so you have to take this into account when you look at the habitability zone around the star. And so if you take, this is for the Sun and one of the stars, this is 581, this is 0.1 the mass of the star, this is 1 solar mass, and this is the distance in astronomical units, and you see that the habitability zone is evolving according to the mass of the star. Habitability zone in our solar system is nearly between Venus and Mars, which is quite nice because we are inside. It's good. And it doesn't mean again that you cannot have some satellites with life. This is possible, but you need some external heating. I mean, not the solar heating. So this is the habitable zone for this system. This is one of the systems for which it has been debated a lot. In fact, before it's like this, but now it's like this. So some planets that were in the habitable zone now are not meant to be in the habitable zone. Then you have to take also into account the greenhouse effect and things like this. So it's more complicated. This is a more elaborate version of this plot. So you have the mass of the star. The Sun is here. This is the radius of the orbit. So the Earth is here. And you see that this is the radial velocity, the transit in violet, and macrolensing in blue. And what you see is that you have the habitable. So this is a dry terrestrial planet in sort of green. This is the Earth-like planet, and this is the hydrogen atmosphere planet. And here you need some internal heating. So if you are close to Jupiter, Saturn, etc., you need some internal heating. So you see that we don't know many exoplanets inside the habitable zone as we define it yet. We'll find some more. We'll find some more. Okay, I go on. This is some potentially habitable planets. You have a website which is the phe.org, I think, where you can find these planets. So you have an updated list of exoplanets that are potentially habitable. For comparison, you have the Earth here. Here you have one that you must know, which is Proxima Centauri. Okay, I will speak a bit later about this planet. It's an interesting system, also because it's one of the, well, it's the closest, so it's which is why it's a bit exciting. And you see that the potentially habitable exoplanets are all rocky planets at a good distance from the star, depending on the luminosity of the star. And now it becomes a bit more complicated. So this is the same plot as before, but more elaborate, more accurate, with the stellar temperature and the stellar flux. Stellar flux 1 with temperature of nearly 5,600 kelvins, the Sun. The Earth is here. Okay. Then you have different colors. This is the Venus case. Venus is here, in fact. Venus case. This is the runaway greenhouse, so it becomes it is becoming too hot, running greenhouse, and this is becoming too cold. So this is Mars, for instance. Mars is here. It is at the limit. So early Mars, maximum greenhouse. Then the sun, the star has not enough flux and temperature to warm up the planet. On the size, you have the subterranean planet, Mars size, terran planet, Earth size, super terran, which are the super Earth or the mini Neptune, the Neptunian, the Neptune size, and the Jovian. And you see that there is a plethora of exoplanets. So this is a plot that shows you a bit more realistically the habitability zone for the planet.
Where is the Earth?
The Earth is here. So one stellar flux, 5,600 Kelvin. So we are happy because the Earth is inside the habitable zone with the greenhouse effect. But this depends on the stellar flux. As I said, the stellar flux has changed a lot, by 25% since the beginning of the Sun, so this changes. And when the temperature of the Sun is changing, the atmosphere of the planet has to adapt, or not, to this.
Why the chance of proximal singularity to be habitable is greater than, I cannot see the numbers from here, but there is a terran planet in about 0.85 stellar flux and 3.2, yeah, this one.
Why is it? No, I don't think those chances are higher. The only thing that Proxima is closer.
I mean, comparing to the previous figure,
This one?
yeah, okay. Okay, I mean the Earth similarity, that's why it's greater for the Proxima Centauri and not for the other planets.
Okay. I didn't really mention this, but the Earth Similarity Index is an index which is very controversial and based on many parameters. Parameters are the stellar flux, the cosmic rays coming from the star, based on the greenhouse effect, based on the radius, mass, etc., presence of the atmosphere. So there are many things that are entering this, so they are producing this, but again it's very controversial. So I think they are happy to put Proxima Centauri with the higher AZ, but
we'll have just one parameter in this slide. So
well, exactly, yeah.
Here we have mostly the
Yes,
greenhouse.
here you have everything. Just to show you, this is just to show you that it's a bit more complicated.
Yeah, okay.
I think I managed. Another plot that shows you how this can be complicated. This is temperature versus the mass, and you have here different planets. So this is the Earth here. This is the habitable zone. You have the so Earth mass planets, super Earth, Neptunes, Jupiters, and brown dwarfs. Okay. These are the low mass stars, very low mass. Well, here you have also the poofy planets. I like this. The poofy planets are like planets that are nearly the mass of Jupiter, but with a high temperature. So the envelope is increasing a lot because you have a lot of evaporation. So in French we say that you have the super poof. Super poof planets are the planets for which you have very big heating, and so they are very big atmosphere around the. They have a very big radius, but which is just caused by the evaporation of the atmosphere. The super poof. So puffy planets. Okay, so this is the planet radius versus the planet mass with different composition. This is only with hydrogen envelope. water, rock, iron. I think I showed you already a version of this plot for a particular planet. This is the number of giant planets with orbital distance and the orbital eccentricity. Which is interesting also that we find many planets which have a big eccentricity. So in the solar system, most of the orbits are very circular. I mean, the orbit of the Earth is nearly completely fully circular. The only thing that vary is just like the Sun is not at the center of this circle. It's on one of the. It's a bit. Well, it's not exactly at the center, so this is why we don't have the same number of days in all the seasons. But the orbit of the Earth is really circular. And this is the fraction of stars with the planets, and you see that nearly 10% of the stars now are observed having planets. We think from the last census that nearly 50% of the stars have a planet, which make a lot of planets. Okay, now we are entering a bit more in the models that we can make from these planets. This is the planet radius versus the planet mass. Earth is here, Venus, Earth, and we are on this blue line, which is made of silicates. We are in between iron and silicates, magnesium, silicium, O3. Okay, this is 100% iron, and then we have other models where you can have 50% silicates, 50% water. We have some candidates here. 25% silicates and the rest of water, or 100% water. And we have some planets that can be adjusted by these different models. So this is interesting because we can begin now to work on the composition of these planets. On the planets. This is not the atmosphere, this is really the planets. And this is something like that I love very much. This is how we could see the Earth if we were very far away. Like 10 light years, and you take a spectrum of the Earth. This is what you see. This is what you see, and what you detect here is some lines of oxygen 3, oxygen, and water. So just by looking at this spectrum, you can know that the Earth is a planet that could be habitable. Because, well, if you have detected it, it means that you have the mass of the radius, so you know it's a rocky planet. From this, you know that there is an atmosphere, and there you know that there is some water, there is some oxygen, so it means that the photosynthesis was processed, and you have some ozone. Ozone stops the UV, so it makes that you can have some life on the. Well, you don't know if there are some rocks that emerge from the water, but if you suppose that there are some rocks that emerge from the water, then you have some life. You can have some life on the rocks. So this makes this planet very interesting for the people that are observing us, if there are some. So this was the a spectrum taken from the epoxy mission that was sent to a planet, a comet, and that took a spectrum, infrared spectrum of the Earth. So I think this is very interesting. And now, before finishing, I will just describe a bit the Proxima Centauri B system, which probably you have heard a lot in the media. Proxima Centauri, so it's the star which is the closest from the Sun. It's a triple system. So Proxima Centauri is one of these triple system star. And what's interesting here is that, so you have in fact the triple system is here. Okay? You have two stars. These are artist view. This is the radial velocity, which shows you that there is a planet around one of these stars. And so these are artistic views. Probably they don't have anything to do with reality. In fact, we don't know. When you look at the models, you don't know at all what is the composition of this planet. And I think this is probably the most important thing, most interesting thing, that we have some models, but we are really at the beginning of knowing exactly what is the composition of this planet. This is the radius versus the mass. So again, you have different models. 100% core. This is Mercury type, Earth type, 100% mantle, 50% mantle, 50% water, and 100% water. So this is Venus, Earth, some Kepler planet, Kourou planet, and here you have Proxima b. Proxima b, in fact, you don't know if it is a Mercury planet heated by the star, which has a quite high stellar flux on many cosmic rays, many UV, very luminous star. So we don't know if it is a rocky planet like Mercury completely burned out, or if it is an ocean planet, which is not exactly the same thing. In this case, here, you have a planet completely covered of water with an atmosphere, where you could find some dolphins swimming in the sea. So it's completely different. So this shows exactly that be careful when you see some artistic view of these planets. It can be. Then you have to look to the paper and see exactly what's inside. Yeah, just I forgot to mention that this is a 11.2 days planet, so it's quite close to the star, which means also that it's probably the life is not easy on this planet. Just to insist, this is the closest planet. If you go with the spaceship that we have now, we can reach it in 70,000 years. So it's a lot. But probably you have heard about the breakthrough science. You've heard about this? It's Milner, I think he's called. He's a guy who is very rich, and he proposed to launch some very small spaceships with laser to send them at I think it's 20% the velocity of the light. And so, yes, 20%. And so instead of going there in 70,000 years, you would go there in 20 years. There you take some pictures, send the pictures back. They come back in 4 years, because it's 4 light years. And so in 24 years, sorry, you would say what is the planet exactly, if it's a Mercury planet, ocean planet, something like this. So the idea is to send some spaceship like this and go there quickly. Okay, atmosphere very quickly. This is the atmosphere that you can detect when you have a transit. You detect them better in infrared because it's more related to the temperature of the planet. And we have now some information about the atmosphere of this planet. This is with, for example, with a Spitzer satellite looking infrared. And we can even do some atmospheric simulation of some exoplanets. So you can see here we can even know if the atmosphere is transparent or if there is some haze, some clouds in the upper atmosphere. And so we have some simulations now for different exoplanets. Again, be careful with the simulations because it might be wrong, but it's interesting that we begin now to do this. And for instance, here we have a transit of an exoplanet in front of the star, and we can interpret this transit with the planet which passes in front of the star, so an eclipse. Then you have the planet light which sums up with the star's light, and here the planet passes behind the star. So all this part is in fact the light from the planet. So we can reconstruct from this the spectrum of the planet, and if the planet has an atmosphere, this light is exactly the light coming from the atmosphere of the planet. Okay, very quickly, I finish in 3 minutes on the observations. So I showed you many observations from the DLT. So this is the Paranal Observatory, where you have this 4 8 meters telescope. Now we have some new techniques of observation that allow us to, even when you have a telescope on Earth, on the ground, you can we can have some active optics and adaptive optics, which allow us to get rid of the atmosphere, literally. So we have some images that are better than for the Hubble Space Telescope, just because we have a bigger diameter. This is 2.5 meters, this is 8 meters, so it's quite nice. Many observations that I show you coming from the Cours, it's a CNES French satellite observing the transits. Kepler has completely revolutionized the field. Kepler is a NASA satellite which has, I think, detected something like 2,500 exoplanets. So it's really huge, and there are still data that are being worked on now. The next satellites, there is one which will be launched by the NASA, which is TESS, satellites looking for transit. Another one launched by the European, which is Cheops, again looking at transit. These are, both satellites are really dedicated to exoplanets. There is then the next year will be the James Webb Space Telescope. This is a 6.5 meter telescope. This one will not be dedicated to exoplanets, but there will be observations of exoplanets. So you see here the Earth and Moon. So this satellite will be put at 1.5 million kilometers from the Earth at the Lagrange point, and deploy a shield, a thermal shield, and observe with this. So it's 6.5 meter telescope. It doesn't fit in any rocket. So you have to fold it. You have to fold all this mirror here, and then go there at 1.5 million kilometers from the Earth, and then deploy the mirror. So it's a challenge. So this will be the successor of Hubble Space Telescope. Plateau will dedicate instruments to observe. So this is ESA, and this is 2024. And then in 2026 we'll have the 38 meter ELT telescope, probably also the TMT, but we don't know where it will be installed. This is the ESO. So here you have someone speaking, and this is 38 meter telescope. This will be the biggest telescope. Again, it's not meant only to detect exoplanets, but it will have a big contribution to exoplanets. Okay, these are all the planets. You have a nice, you even have some music. You have a nice, this is Kepler, so you have different velocity, different, you have the multiple systems, you have some small systems, you have some systems which are very big, etc. You have the diversity, it's quite nice. So you can look at this for hours, but probably I will stop. And obviously, it's just the beginning of the history, because we will try to characterize better the atmospheres and try if we can find some life. Probably the life we will find will not be exactly like this, but even, as I said, even if we find some microbial life, perhaps that we will find it before on Mars, we don't know, or on another satellite like Titan, or I don't know. But it's interesting to look at to characterize all these systems. And I put my last slide, which is all the bibliography that you can where you can find some more information. As I said, I have the PDF. The whole PDF is online here. So if you want to find it, don't hesitate, and you have also my mail if you want to send me some questions afterwards. Thank you very much for your attention and for your active participation.